Today we're going to learn the last few sections of this chapter. In section 7, we will study constant force of interest. This is basically the limit case of the m's compounding when m goes to infinity, which we already had a quick look at a few lectures ahead. So here, let's start with the question, okay? So we know when the number of compounding frequency m increases, the accumulated value increases as well. So a natural question is, what will we be getting if m goes to infinity, right? So to answer this question, we need to basically look at the formula. So let me write it down here. AVT equals, well, so you can either put x or assume x is 1 plus I m divided by m. Here is mt. So what we want to know is when m goes to infinity, what would be my AVT, right? So for simplicity, we can set x to be 1. In other words, we are considering AVF, okay? So from the calculus course, we studied something called Taylor expansion, okay? So Taylor expansion is a technique to expand any function in form of power function. So as you can see here, all the functions are in power form, okay? You can think 1 as x to the power of 0, okay? So this is how you can express an exponential function using standard polynomial or standard power function. This is obviously a power function. Sometimes we also call this polynomial. So we are trying to use a sequence, well, it's an infinite sequence of polynomial functions to express any given function. So here it's exponential. This is the form. In case you don't know, you can check your calculus textbook. But this is not important. So if you really don't know, that's okay. Okay. So if you really don't know, you can skip this. All I want to give you is actually this result. Let's take a look. Define two sequences, A and B. A is defined as 1 plus 1 over n goes to the power of n, and B is very similar, except the power term now is n plus 1 instead of n, okay? So we can actually show that both sequences converge, and they converge to the same number, that is E. Sometimes we call this Euler's constant, right? So this is the standard base for the exponential function, which shows here, which means if you take x to be 1, so e to the 1 obviously is e. So this is the limit of this sequence. It takes some time to show why A and B converge. So basically, both of them are monotone sequences. One of them is increasing, the other one is decreasing. You can check which one is increasing, which one is decreasing. And obviously, we know this is obvious, right? So let's say if you have this, let me do it. So here n is, so both here in A and B, n are natural numbers, which means they are 1, 2, 3. So you can plug in a few values to get a quick sense to see which one is increasing, which one is decreasing, and plug in a quite big number of n. Let's say n is 100 to see what is A 100, what is B 100, and use your calculator to get the constant e, so which means you can take the exponential of e, okay, and at the e of x at 1, This is roughly 2.7 something. Okay, so try to see whether A100 and B100 is somehow close to the exponential. Okay, so it's easy to check, but I'm not going to prove here. If you are interested, you can probably consult some calculus textbook. So the key result, which I just mentioned, is the limit result, right? So it's here. So if you look at this, where is my AV here? If you do a quick comparison, they are nearly the same, right? All we need to do is, so I keep writing in this place. Forget about x. I can write this as, so m divided by I. Okay, I need, you can think this as n in this place, right? Then I need another n down here. This is not exactly what we have. What we have is mt. So in order to get back, I need to times by I t, right? And according to this result, things down here, the limit goes to e. So when m goes to infinity, this is basically e to it, right? So this is what we have. So that's exactly what I put down here, except I no longer write it as I of m, right? So that's basically what I write. Right now, we define, okay, a continuously compounded interest. So that's basically when m goes to infinity, that is continuously compounded. Again, m is, you separate 1 year or 1 period into m equal periods, right? So it's 1 over m, 2 over m. So which means you compound m times a year. When m goes to infinity, that means you get interest almost every instantaneous amount of time, right? So that's the concept of continuity, continuous, right? So things can no longer be separated, can no longer be like partitioned in this nice way. The gap between two units, between two unit times becomes smaller and smaller. Eventually, you will not be able to see it anymore, on the timeline. That's the limit, which we call continuously compounded. Okay, a continuously compounded interest rate sometimes, often, is called the force of interest. And we have a new notation. We don't want to use I. We want to use delta. So this is a Greek letter. It's called delta. So in the future, we will simply say the force of interest is delta. If this is delta, that means equivalently, I have this definition. So you can simply see this as the definition for force of interest or the continuously compounded interest. Okay, given the force of interest being delta, your accumulated value at time t will be equal to x times exponential of delta t. So you can think this as the definition. And that is something we're going to use in the future. So to see the connection between delta and I, we can simply let t to be 1. So in that sense, okay, this is the total amount or the AV value of $1 at time 1. So if I apply effective interest, so my $1 at the end of 1 year will be 1 plus I. So when I equate them, I can easily see the result is log 1 plus I, right? So this is effective. So if my I is not the effective interest rate, but rather the m's compounding interest rate, so I will get this formula, okay? So here I is I to the m, okay? So it's the nominal interest rate of m's compounding interest rate. Of course, in the particular case, which I already derived, is already here. So this is the quick connection between delta and I. So here we have a little further understanding This is not exactly needed, but it's helpful to see the three forms of interest we have studied so far, right? We have studied simple interest, we have studied the compound interest, we have studied the continuously compound interest. So in the end, everything boils down to one function, okay, which I call the accumulated value. Okay, remember we used to use AV to denote accumulated value, okay? Here, I further introduce a small a. So the meaning of this small a is here. So that is basically the meaning of small a. What is the accumulated function? Accumulated function gives me how my account value grows over time. Right? Remember, x is simply the principal, the starting value of my account. So all I need on this new function is it should be increasing, okay, in the sense that when times moves forward, the amount of money in my account should be growing, right? So that's why it's increasing, okay? Continuous simply means the value does not jump. So my money today, let's say it's $100, it does not jump to, let's say 105 in the next second, right? So we want something continuous, okay? And obviously we want A0 to be 1 so that X is indeed my original amount. Here I give you three possible examples: linear function, power function, and exponential. Okay, each corresponds to one form of interest. The first one is obviously simple interest. The second one is compound interest. The last one is continuous interest. Right? Of course, there are many, many more choices. Right? You have studied a different form, a wide range of functions which are increasing and continuous, right? So in fact, any combination of those, still a candidate. So you don't have to be either one of the form. For example, let's say I can give you this. P is 1 minus P. Right. So this is a mixture of two continuous um, accumulation functions. Okay, the first one at rate delta 1, or force of interest rate is delta 1. The second one, force of interest rate is delta 2. You can combine many functions fitting those properties, okay, to be a candidate for accumulated function. Once you have accumulated function, you implicitly define a new interest, okay? So we can obviously set x to be 1, and then your AV function will simply be a. Now, let's further assume x is differentiable, okay? We can easily get this result, okay? Obviously, it's on the right-hand side, you apply the chain rule, right? So you do the outside function, which is log function. When you differentiate log function, log x is 1 over x. Of course, x has to be positive. And by the chain rule, we get log is the outside function. Okay, so the first layer, I get this. And because of the chain rule, I also need to differentiate the inside function, which is a, right? A ply means the first derivative. So a ply is the first derivative of function a. Okay, so we can easily see when a is given in this form, the a ply over a is nothing but the force of interest. That is why it is called the force of interest. Okay, if you study life contingency, you will know this is also called the force of mortality. But there, a is not accumulated function. A is your survival function, right? So now let's study some quick examples. There are quite a lot from the homework. At least there are 3 examples plus one small one. It's not labeled as an example on page 18. I think they should be very straightforward. Let's see, 1.18. If the constant force of interest is 6%, so delta is 6%, what is the corresponding annual effective rate of interest? Annual effective interest rate is I, which is log, not log, so which is in this form, right? Left-hand side denotes the principal plus effective interest rate. So that will be the value at 1. So it's AV1. AV1, okay? Assuming X is 1, okay? The same one. This is how I calculate AV1 by using continuously compounded interest rate. So you can easily solve this to get, you can get the result. Okay, 1.19. So I know the force of interest rate is 4.2%. Calculate the present value of a payment of 1,000 to be made in 8 years. So I know AV8 is $1,000, and I want to know the present value. Okay, let's use X to denote E to delta T. So this is the AV formula. I have a typo here. It's 8. It does not, shouldn't be looking like a delta. Okay, so let me plug in. This is 8, right? So I can easily get the result. By the way, in the future, you don't need to write this formula, right? You can just use the negative power, which means if you are moving forward, it's positive power in the exponential. If you are discounting back, it's simply negative delta t. So it's very easy. I will leave 120 to you. The next section, we study varying force of interest. Okay, so your delta is no longer a constant. So your delta is a function of t. Okay, so here delta t equals a constant. So that is the difference. So the interest rate changes in section 8, well, which is slightly more practical because the interest rate does change, right? So here, what will change? So basically, the idea is still the same, right? So we can still write this down. This goes from the previous argument that the force of interest is the derivative of the log function of AV, or you can see is the derivative of AV divided by AV. So this is the setup, or somehow the definition of force of interest. This is more general. This is a more general definition of force of interest. Okay, so from there, we apply, the standard theorem in calculus, right? We integrate on both sides. Okay, from T1 to T2. So I have my left-hand side here. And when you integrate on the right-hand side, it's exactly log AV at T2 minus log AV at T1, right? And using the rule of log functions, log A minus log B equals log of A over B, right? So I'm using this property. And from there, okay, once we have this equation, I apply exponential on both sides, which means I have exponential, and the log, they are the inverse functions, right? If they are the inverse functions, you get, it somehow, you cancel both of them, right? So I take T1 to be 0, I take T2 to be T, then I have this formula, right? Of course, I'm going to times X or AV0 to the other hand side to write this equation, right? So basically, everything is still the same, except it's no longer a constant. Remember in the beginning or in the previous section, this is my AV formula, right? Now, because my delta is no longer a constant, okay, the area, you know, what it accumulates is no longer a constant down here. I will need to change this into the integral from 0 to t delta s ds. Obviously, if delta is a constant, this goes back to this, right? When you have a constant force of interest. So pretty much you can, if you don't understand why I have this, that's completely okay. Simply treat this as a definition. So if you don't understand why I have this formula, treat this as a definition, right? And the somehow the difference between the previous section and this section is that here you have a constant, here you have an integral. Okay, that's because delta is a function, right? And you cannot use function times a t. That function is value. What you get is an integral. Some examples. The difficulty in this part is pretty much calculus. Okay, so for instance, let's try this. $10 is invested time 2. $10 is invested at time 2 years using a force of interest is 0.2 minus 0.02 t. So this is the force of interest. As you can see, at time 0, the force of interest is 0.2. As time moves forward, it gets smaller and smaller, okay? It's even negative beyond 10 years, okay? But luckily, we don't need to deal with 10 years. Everything finishes here at the end of 5 years. Okay, so I want to know by the end of 5 years how much I will be able to withdraw from this account. So the textbook put this notation. The meaning is basically obvious because it says from the initial time to the end time. Okay, so we can write something even more general. Remember, all we need to do is to integrate, right? So this is the part, right? It goes from T1 to T2, and it's the integrate of the it's the integral of the force of interest rate function, okay, with respect to time, obviously. So at the beginning, I have $10. Okay, now I am. By the way, sometimes I use EXP, sometimes I write E. They are the same. So now from 2 to 5, 0.2 minus 0.02t dt. So in the end, this is a calculus question, right? So let's continue. Let's finish this together. No, I'm doing antiderivative. So a constant gives me t, and here is a power function, goes up by 1 and divided by the power, right? So if you forgot basic calculus, you really need to go back, okay? You should be able to do the both the derivative and antiderivative, okay? So there are some formulas from calculus. Okay, so you need to check. Once we have this, the meaning is I plug in 5 minus 0.02. So you know when you divide, it becomes 0.01, right? So let me write 0.01. 5 square, which is 25, minus 0.2 times 2 minus 0.01 times 2 square, which is 4. Okay. So when I compute everything inside, that is 0.75 minus 0.02 36. So then you can continue, right? The next question is, I know the future value. I want to go backwards. How do I go backwards? All I need to do is to put a negative, right, when I do the integral. So this is really simple. So I know at the end of 8 years, my account value is $200. Okay, I want to go back to year 3. So I want to get the PV value. Okay, so I actually like the notation in this section because from here I can see the starting value, I can see the end value. So my end value is 200. Okay, when I write the integral now it's negative because I'm discounting, right? The when you divide by an exponential, you get negative. So basically, if I divide by this, what I be getting is this, right? So that's why I have negative. My force of interest is 0.1 minus 0.002t dt. So again, it boils down to doing this integral. Okay, I believe this should be straightforward, right? And in most questions I see from this course or from financial math, the force of interest usually is in polynomial. So you're dealing with power function. Okay, so it should be straightforward. Okay. Let me stop here for this, and we will finish this chapter in the next video.